Astronomy is a fascinating subject for so many people, whether they're chasing eclipses, studying star charts, or stargazing at night. What you may not know is that we can gain a lot of information about stars just from studying their light. What is light? Light is an electromagnetic wave, a combination of oscillating electric and magnetic fields that travel through space. Visible light forms only a small part of this whole electromagnetic spectrum, which is divided into groups by wavelength. The shortest wavelengths in this electromagnetic spectrum are gamma rays. Then, with slightly longer wavelengths, come X-rays and then ultraviolet waves. The visible light spectrum is next. Then, after visible light, comes infrared waves, and as we get finally longer and longer wavelengths, we approach microwaves and radio waves. The Sun is a massive source of electromagnetic waves. It radiates plenty of visible light, as you can see around us, but it also emits in other parts of the electromagnetic spectrum as well, such as ultraviolet radiation, which is what makes us tan or burn, and infrared radiation, which heats things up. The Sun doesn't emit all of these wavelengths equally. In fact, it's useful to plot a graph of intensity versus wavelength. When we do this, we see that the Sun emits radiation of wavelength 500 nanometers most often, and shorter and longer wavelengths with less intensity. But where does the Sun get all this electromagnetic energy from? As the laws of physics tell us, you can't get something from nothing. The Sun gets its energy from fusion. Fusion is the process whereby light nuclei combine to form heavier nuclei, releasing energy in the process. In the core of the Sun, hydrogen combines together to form helium, yielding enormous amounts of energy. While the Sun's light may appear to be yellow or white, as we said, it is made up of many different wavelengths in the electromagnetic spectrum, including all the colours of the rainbow. We can use a prism to split the Sun's light into these component colours. Long visible wavelengths around 700 nanometers look red, while short wavelengths around 400 nanometers look blue. The Sun is the star we're most familiar with, but we can split light from other stars in a very similar way. The technology we use to do this is similar to the prism that we were just using. Things are a bit more complicated for distant stars because they're far away. First of all, we need a telescope to focus the image. Then we use a spectrograph, which splits up the light by its wavelength so we can study its various components. When we do this, we find that not all stars look like the Sun. Some have more blue light, some have more red. But when we plot the intensity of the light versus the wavelength, all graphs have a similar shape. In fact, everything that is hot emits electromagnetic radiation with this characteristic shape. The hotter the object is, the more the peak wavelength moves towards the blue area. The cooler the object, the more it moves to the red area. You'll notice that hotter objects emit greater overall intensity in all parts of the spectrum. These graphs aren't exactly what we see from stars though. If we look at a real stellar spectrum, we see that some parts of this spectrum appear to be missing. The curve is not perfectly smooth like we saw before. Why are certain wavelengths so low in intensity? Well, just like the Earth, stars have atmospheres of relatively cool gas. This gas can absorb certain wavelengths of electromagnetic radiation. Different gas atoms absorb light of different wavelengths. So we can say which elements are in the atmosphere of distant stars just by seeing what wavelengths are really low, which ones have been absorbed. We call these absorbed wavelengths spectral lines. Looking at these graphs, called stellar spectra, astronomers decided to group stars into spectral classes based on similarities among the pictures. There are 7 general classifications, labelled by the letters O, B, A, F, G, K, and M. This might seem a bit tricky to remember, but people have come up with a range of mnemonics like "Oh big and furry gorilla kill me" or "Oh boy, Astronomy final's gonna kill me. The O-class stars are the hottest and the brightest. They are known as blue giants and have surface temperatures of 20,000 degrees Celsius or more. We can identify these O-type blue giants because they are the only ones that show absorption by ionized helium, and they have strong emission in the blue part of the spectrum. Stars in the B, A and F classes are cooler and appear yellow or white. These B, A and F stars show strong absorption by hydrogen. Our own Sun is a G-type star with a surface temperature of about 6,000 degrees. The K and M stars are the coolest stars within this classification system. With surface temperatures of around 3,000 degrees, they appear red. Looking at stellar spectra, we find that the spectral lines aren't exactly where we expect them to be. For some stars, spectral lines are shifted to the red part of the spectrum, while for others, they are shifted over to the blue part of the spectrum. This is called redshift or blue shift. To understand why this happens, think of a car moving towards you honking its horn. As the car gets closer, you hear the horn at a higher pitch than if the car were still. But as the car passes you and starts moving away, the pitch of the horn drops and the tone is lower than if the car were still. It is the same with spectral lines. Redshift would indicate that the stars are moving away from us, while blue shift tells us that they are moving towards us. The magnitude of this shift tells us how fast. You can also tell how fast a star is rotating by looking at the width of the absorption lines. For stars of a given size, a very fine, sharp absorption line tells us that the star is barely rotating. The light from all sides of this star is equally redshifted. But if a star is rotating quickly, then we see a wider absorption line, because one side of the star is moving towards us and the other side of the star is moving away. Light from each side is redshifted by different amounts. So simply by looking at the light produced by distant stars, we can find out a lot about them. All we need is a telescope and a spectrograph. Who knew you could find out so much about a star simply by looking at it?